Hello and welcome to another tutorial. In this tutorial I'm going to continue our discussion on sequences and series, and in the last video we discussed what sequences are. They're just a simple representation of functions over the integer numbers, and then we discussed also a particular type of sequences which are recursive sequences, and now we're going to look at another type of sequences which is called a series. So series is basically a sequence that is defined as the sum over another sequence. So if AI or AN is my sequence, I can create a sum from index I equals k to n and call this S of n. So with this definition saying that my series has an index n, it means that I'm fixing the initial index, which is k, and just I'm varying the final index n. Okay, so this sum basically means that I'm summing Sn is equal to ak plus 1 all the way to an. And if you're wondering how many terms are in this sum, it's last index minus the initial index plus 1. And the plus 1 is because both the last index and the initial index are included. If one of the end indices is not included, we have n minus k terms. If both indices are included, we have n minus k plus 1 term. Okay? And remember that I is the summation index. So when we use the sigma notation, it just we use some summation index, which is I, and it runs from k to n, and the series S is defined over the last index n. Okay, so a series is a sum over the terms of a sequence. So if a sequence is given, then we can sum over its terms, right, from some number to some number. And typically k, the initial index, is 0 or 1, and n runs over the positive numbers 1, 2, 3, etc. So the sequence usually starts from 0 or 1 or 2, something like that. Now in order to evaluate Sn, obviously we have to calculate a first, all the terms that we need from the initial index to the last index, and then sum them up. Okay, now what you can see that there's an element of repetition. What do I mean by that? What I mean is that if I calculate S5, for example, and the initial index is 1, I have to calculate A1, A2, A3, A4, A5, right? Now let's say I want to calculate S6, then I have to calculate A1, A2 all the way to A6. But A1 to A5 were in fact calculated when I evaluated S5. So I do not need to actually recalculate them each time that I'm trying to calculate some S at some index, right? So what we can do, we can use some concept called caching, and which means that when for the first time I evaluate Sn, I'll try to save ak plus 1 all the way to an. All right, and then if I want to evaluate S at some other index, let's say Sn plus 2, when I start to look into the a terms, ak all the way to an plus 2, I try to see whether or not these terms, each individual term, has been calculated before or not. So caching means that the first time when a is calculated, just calculate and save it into some hash map or something else, a data structure. Okay, and then next time I want to calculate the sequence, I'll try to see if any of those terms, a terms, have been calculated before or not. So if they have been calculated and saved, I just retrieve the values. I don't calculate them again. So this can in fact save a lot of performance, and this shows itself especially when we look at the Fourier series or series of functions, because then if I want to evaluate a function at say 1000 points, I do not need to calculate all the coefficients 1000 times. All right, now just like sequence, there is a limit concept of Sn, a series. So when n goes to infinity, if the value of the sum approaches some number, we say that that number is the limit of the series, all right? And mathematically, this means that when at some point n, for some large index n, the difference between each two terms becomes less than some arbitrary number epsilon, we say that the series is converging, and we can find the limit. If this doesn't happen, we always end up with some number, then we say that the series is diverging, okay? So, and then for example, one case is that if an is monotonically increasing, then series always diverges, right? And in fact, there is a lemma, or there is a theorem that says that the necessary condition for a series to converge is that the sequence approaches zero when n gets larger and larger. That's the necessary condition, not enough. Okay? And so there are other conditions that need to be satisfied. But if the limit of the sequence is not zero, we are sure that the series does not converge, okay? And if we want to calculate, so we can define the series as the sum, as a sequence, but then if we want to calculate the infinite sum or the value of the series or the limit, we can define plus infinity and negative infinity. And we can just use a enum type for such a thing. And the other thing is that obviously we cannot sum infinite number of terms, so we have to cut the series at some point, and for that we need to have a convergence test, or what is the tolerance or the error. Convergence test is basically defining the error of the evaluation. And we can have an absolute error or a relative error. Relative error is when the next term becomes less than 1% of the previous term, we can cut the series and consider it a convergence. Absolute error is when the difference between the two terms of the sequence of the series is less than the error, then we call it a convergence. All right? Let's head to Eclipse, and I'm going to define an enum type. I call it limits, and here I'll have the infinity, like plus infinity, minus infinity, or positive infinity, negative infinity, positive infinity, and negative infinity, something like that. And I'm going to create a class called series. All right, and in this series what we are going to do is we are going to have a method called public double evaluate, or get value, for example. And here we're going to pass a sequence, and then we're going to have initial int. We have an integer for the initial index, and then int for the last index or the final index. All right, so final is a keyword, so let's call it last index. And then you can probably guess what we're going to do. We create a double value result, and then eventually we need to return the result. And in the simplest form, we just write a for loop. For int k equals initial, and then k less than last plus 1. Remember, we want to go all the way and include the last index, and k plus plus result plus equals sequence dot evaluate at k. All right, this is how we calculate the series, a finite series. So this is for finite series. And then let's go and test this. So I'm going to create a new class called test series, and I want to have a main method. And here I'm going to create a series. So the first approach is create a sequence and pass it to series. So sequence sec equals, let's call it sec1, equals new sequence, use the anonymous class, and then we need to implement the evaluate, and here I'm going to say k, or I don't know, 2k, and then we create a series object, series series 1, new series, and in the constructor we don't pass anything, right? And then double val1 equals series 1 get value, I pass my sequence and the initial, let's say from 0 to 5, and then run a system out.println val1. All right, let's see what happened here. So we created a sequence and we used the anonymous class approach. Remember that sequence is an interface and you cannot instantiate interface, but anonymous class allows you to do that if you implicit or explicitly override the value, the method evaluate, which is an abstract method. Remember, evaluate is abstract method in the interface, in the sequence interface. All right, and then we create our series class, and the series class takes care of evaluating the sum over some sequence from the initial term to the end term. Remember that both the initial, both ends of ends of the sum or indices are included. Remember that, because in some languages such as Python, there are predefined functions. When you say create a distribution of integers from 0 to 5, the convention is to include the first index but exclude the last index. But here my convention is that I'm going to include both of them, because that's closer to the way we write the sigma on a paper, right? When you write from 0 to 5, you actually mean that the first term and the last term are included in the sum. So if I put here just k, and then we end up with half of it, 15, that is correct. And then if I put -1, it also works, because actually it doesn't work, because the for loop only goes from increasing, right? So if we want to be able to sum over in each direction, basically when we say 0, -1, we also calculate from 0 and then -1, -2. We can modify it here. So this is the sum evaluation. This is the check for proper limits or proper index values. By that I mean that we check that if initial is greater than last, then what we are going to do is we can probably define local variable int init lst, if initial is greater than last, what we're going to do, say that init is actually lst, init is the last one, and the lst is init, right? We're swapping the otherwise we're going to say init is initial and the last is lst, and then here we put init, or basically lst is last and lst. Alright, let's see this works. Yes, now if I say from 0 to -5, it should return -15. Okay, or if I say -5 to 0, it should return. Now what happens if the two indices are the same? Does it return -5? Yes. So 2, 2, 2. And the reason for that is we included both the initial and the last index. That's why we have last plus 1. So k runs over from the initial to last. Okay, but now the important thing here is that caching. So as you can see here, each time we evaluate the term, we can run into the problem of the fact that we have to evaluate all the terms of the sequence all the time, right? But this is not recommended. So what we're going to do, we're going to change this to static, because here this function doesn't have anything to do with class, right? We define the sequence, we define the initial and the last, and then obviously we get a warning here because we're accessing the series by an instance, but get value is a static method, and you have to access the static method via class, not the instance. So we have to use the series class. Alright, in fact we don't even need this. I'm going to highlight it, and this still works, right? Get value sequence from here to here, and this still works, but this is not efficient. So what we're going to do is we're going to create a constructor here. So basically create an instance sequence, alright, and obviously it gets initialized to null, or we can specifically or explicitly set it to null, and then I'm going to have a constructor, and here I'm going to pass a sequence, and because I'm using the same name, I have to use the this reference to make sure that no shadowing, so no shadowing of global variables, because I'm using the this term. Okay, now I have this. What I'm going to do, I'm going to basically create a map or hash map from Java util, and it's an integer, and remember you cannot use primitives in hash map, cannot use primitives in hash map, have to use wrapper classes. So this map is basically takes track of which terms in this sequence have been evaluated. So it should be integer, which is the index, versus double, which is the value. So I call it cache. All right, and obviously when I create the object, I'm going to also initialize it, and we actually didn't need to have a specific map, a specific hash map. We can just use the map interface, and I need to import it from Java util. Okay. Alright, so what happened? We have the sequence, we have the cache, and now when we create something like this, and this is not static anymore, but here we don't specify the sequence because it's been given there in the sequence. All right, and I'm going to assume that it's not going to always, the initial is always less than index, initial and last. But what I'm going to do here, instead of doing this, what I'm going to do is put a if here. So here where caching happens, here is where caching happens. And what do I mean by that? We're going to say that if our cache contains key, and the key is an integer k, all right, if it has, then result plus equals cache dot get k. All right, so if the index k for the sequence has already been evaluated and it's in the map in the cache, then we just retrieve it from cache, and this is a hash map, so retrieval is very fast. Else, what I'm going to do else is now obviously I'm going to, I need to evaluate this, but then basically what I'm going to do is I'm going to evaluate the sequence. I get the sequence evaluate at k and put it in the map. Let's call it x, some local variable. We calculate it. All right, we put it in the map. We also add it to the result. Now what happens here, you can see what happens. So we do the caching. So if term or ak is has been evaluated before, then we just retrieve it. If this is the if first time, ak evaluated, put it in the map. All right, let's see. We use the static version. Now let's actually uncomment this, create series 1, and in the series what I'm going to do, I'm going to create a lambda expression. So k times let's say k. So what happens here is that this is lambda expression or functional, so we're passing the sequence to this, and now we want to see first of all this works. So sysout series 1 dot evaluate get value from 2 to 5. Yes, works, right? Both of these are working, right? But now let's make a comparison, of caching versus not caching. So what I'm going to do, I'm going to write a for loop, I equals 0, I less than integer dot max value, I plus plus, and basically I'm going to time it, right? For the benchmarking, I'm going to time it, and in my mathlib library, my library on GitHub, in the utils, I have a timer. Okay, so you can just use this class, and in order to do that, I'm going to go to the build path of my project, and in the project, I'm going to add a dependency on the mathlib. All right, and what I'm going to do, I'm going to create timer. I'm going to import it from mathlib. Timer1 equals new timer. Alright, and then timer1 dot start, and each time I'm going to evaluate basically from 1 to, or from 0 to I. So we're going to sum this. Alright, and then timer1 dot stop and sys out timer1. Let's run this to make sure it works. It is still evaluating. So 5,958 milliseconds. So it took about 6 seconds. All right. Now I'm going to basically copy this, and this time I'm going to create another timer, timer2 start. But now instead of doing this, I'm going to create use the series that we created, right? So in the here I'm going to say series 1 get value from 0 to I. Now let's see what happens here. And here we're going to have timer 2. Let's save it. So the first for loop is taking time, about 6 seconds. The second for loop is taking time. Apparently it's taking more time than Alright, I'm going to maybe reduce the limit. So let's say 1,000, 10,000. 47 milliseconds, 803 milliseconds. So the overhead that we're paying here is that in this case evaluating the series is actually much more efficient than caching and then uncaching, which means you're putting in the map, in the cache, and then retrieve them, because the sequence here is very simple. But if the sequence was defined in terms of something that takes time, let's say an integral function, and we will look at that when we look at the Fourier series. But if the evaluation of the interval takes time, then we want to use caching. But if the evaluation of the sequence doesn't take time, then better not to cache the sequence. So I'm going to write it here. So implement caching only if the evaluation of the sequence takes time, or basically it's a costly operation. And that's actually the case for Fourier series. So what I'm going to do here, I'm going to set a boolean here, boolean do cache, and I'm going to set it to false. And then we have a setter here, public void set caching flag, for example, boolean caching, do caching. This dot do caching, do cache equals do caching. All right. So, and therefore what we're going to do, we're going to say if do cache we're going to implement the caching thing, the caching algorithm here. Else we're just going to basically get the result so if you're not doing caching, then we can just evaluate the sequence, and if I run this again, hopefully the result is yes, it's the same, because now we're not doing the caching. But we will see a case in the next lecture that when we do the caching, we actually need to we actually get enhancement in the evaluation of the function. All right, so I'm going to put a comment here. So the first timer for access via a static method without caching. The second is a second timer access via instance method, and here caching can be enabled. So right now caching is disabled and we get the same performance, but if we say that series 1 do set caching flag is true, so we add a flag here for caching, then this is going to take a long time, because putting to the map and then retrieving is not the efficient way here. Okay, it's actually less efficient than directly evaluating the sequence. All right, but for the cases when calculating the terms of the sequence is less efficient than reading and writing and reading from a cache, a map, it's better to do the caching. So in general, our series class is better to have this capability to be able to, so that we can turn the caching on and off. All right, and thank you for listening. In the next video we will look at two specific series. One is Fourier series and the other one is Taylor series. I'll see you in the next video.